Fatty acids are a type of lipid. So since they are going to be a type of lipid, they are going to be very hydrophobic because that is a characteristic of lipid molecules. And if we start talking about their structure and how we would recognize fatty acids, these are going to be made up of the same elements as the carbohydrates. So they do contain carbon, hydrogen, and oxygen, but this is going to be in a different ratio or proportion than what we had with the carbohydrates. So what we'll find is that we're going to have lots of carbon and hydrogen, but we're going to have little of the oxygen here. So if we start to draw one as an example, first thing that we're going to have is we're going to have a long carbon chain. So we're going to have lots of carbons in a row. And when I say lots of carbons in a row, it is really a lot. So this is going to continue on here. And I'm just going to draw it like that because we could use the skeletal formula if we wanted. But when we say a long one, we're usually talking 16 carbons plus. So 16 carbons long, maybe up to 24 carbons long, something along those lines. So it is very long. And then we're going to, at the very end, we're going to have one carboxyl group. And hopefully you know what a carboxyl group looks like. But a carboxyl group is going to have a carbon that has a double bond to an oxygen, and then it also has an OH attached to it. So I'm going to draw a carboxyl group at this end here. So I'm going to add one on, just going to face it the other way. And then the only other thing that we have to do is we fill in with hydrogens. So hopefully you're beginning to see that hydrogen atoms are kind of a filler in a lot of these molecules. I'm just going to go around here and make sure that every carbon has 4 bonds. So I'm going to add in my hydrogens so that they will. And again, I don't want to, I'm not drawing this as large as what it would really be. But this is a good place where those skeletal formulas really come in handy, because if we don't have to actually write every C and we don't have to write every H, we could write this a lot faster if we're really just drawing kind of the zigzag line. Okay, but that is a typical fatty acid that I've just drawn here. So for the fatty acids, notice that the vast majority of the molecule, so everything from here on down, that is all going to be a hydrocarbon. So hydrocarbons are only hydrogen and carbon. And that's why we said we're going to have lots of carbon and hydrogen, but we're not going to have very much oxygen, because the only place that we see the oxygen is down here in this functional group, the carboxyl group. What this means is that most of the bonds are going to be non-polar covalent bonds. And that is really what gives us this property of lipids and of fatty acids, the fact that they're hydrophobic, because hydrophobic molecules are going to be primarily non-polar molecules, or molecules that have a lot of non-polar covalent bonds. So that's one example of a fatty acid right there. Now we can take the fatty acids and we can break them into 2 groups. We have ones that we call saturated. I'm going to say a saturated fatty acid, and we can have unsaturated fatty acids. And so the one that I'm going to draw first is a saturated, and this time I am going to use the skeletal formula. So I'll draw my carboxyl group here on the end, but then we're just going to have a whole bunch of carbons here in a row. So that's my saturated fatty acid. That is what we had an example of just a moment ago. So the saturated is referring to the fact that these have the maximum number of hydrogen atoms in the tail. And what I mean by the tail is the long hydrocarbon portion of it. So if that doesn't make sense to you, first off, let's take a look at the unsaturated ones. So if I were to draw an unsaturated one, it is going to be very similar to the saturated, except that now we're going to have maybe a double bond inside the tail. And this might be 1 double bond in the tail, it might be 2 double bonds in the tail. But if we think back to the skeletal formulas and how those double bonds affected the number of hydrogens that could be packed on, if we look, for example, at this carbon can only have one hydrogen coming off of it. This one can have one coming off. All of these other carbons would get two hydrogens coming off of them. This one would only get one, this one would only get one. Right? So hopefully you can see that when we do start to add in these double bonds, that it does affect how many hydrogens we can get packed on here. And so the unsaturated ones, they do not have the max number of hydrogens. Instead, they have at least one double bond. Okay, so at least one double bond. Now, one thing I do want to make sure that we all understand is that when we talk about this double bond, we are not talking about this double bond in the carboxyl group. So that one's always going to be there. The double bonds, we're talking about the tail. So the hydrocarbon area of the molecule, which is everything that is not that carboxyl group. So if there are no double bonds in the tail, we have the saturated ones. If there are double bonds in the tail, we have the unsaturated ones. And if you have one double bond, we can call it monounsaturated. And if we have more than that, we can call it polyunsaturated.